We're supposed to nail the case before we move on to juicy applications, but we're trying to make a quantitative falsifiable prediction. But how can you make a quantitative test of a theory that freely admits that every time you do it, it will be different? Doesn't science demand repeatability? Isn't that what science is all about? And what's an important point? In quite a lot of science, your prediction is actually statistical. It's not telling you what's going to happen every single time. And you can test such a prediction, but not with a single trial. You have to make a lot of trials. The more trials you make, the greater the conviction that you get that your hypothesis is either working or failing. What we're predicting is not how strong a signal we'll get. What we're predicting is the probability distribution, the histogram of what happens over many trials of identical flashes of light. So that light hypothesis and a little simulation like the one I just showed you lets us predict mathematically how much randomness we should expect to see if that hypothesis is true. That's what we can compare to the performance of real eyes. So here's a magnificent tour de force piece of spycraft. It's an experiment done by Dennis Baylor and his colleagues over many years. Here's some retina. You start with a salamander and you move up from there. And got a lot of photoreceptor cells, and one of them has been gently aspirated into this pipette. Here's a highly magnified picture. The pipette is very narrow. One of them has been gently aspirated in that pipette, and you can see what's going on with the cartoon here. There's an electrode inside the pipette. There's an electrode outside the pipette. Current that would have flowed from one end of the cell to the other can't do that because the pipette is in the way. It has to take the long way around, go through the measuring apparatus, and make a measurement. That's how you can measure the response of one individual photoreceptor cell. Yeah, an amazing experiment, okay? You've got to have good electronics, you have to have good spycraft, and here's the results. You send the same flash of light over and over. Sometimes you get nothing coming out. Sometimes you get a peak of 1 picoampere of current. Sometimes you get a peak of 2 picoamperes of current. But you get responses, it turns out, that fall nicely into these separate categories. It's very tempting to suppose that this is a case where no molecules got flipped, one molecule got flipped, two molecules got flipped. Very tempting to suppose that, but we got to do the acid test. What's the acid test? Well, you got to compare that sort of data. You got to turn it into a histogram and compare it to the experiment, to the theory, pardon me. So here's what the theory predicts. If you give a very weak flash of light, mostly you'll get nothing. This is a histogram. Most of the time you'll get 0 picoamperes, and once in a while you'll get 1 and hardly ever 2. If you send in a stronger flash of light, this one's 4 times stronger, you'll often get 0, but very often you'll get 1, and sometimes you'll get 2 and maybe even 3 picoampere current coming out of that. All of those numbers, the heights of all those peaks, those are the multiple predictions of this theory with only one free fitting parameter. And if they pan out, then we'll have strong evidence that not only is the light hypothesis correct, but that it actually matters for our vision. So in the black here, we've got some experimental data. This is a histogram. It's drawn like a histogram. It lies right on top of that theoretical prediction. It looks like a promising theory. That's not Baylor's original data. It's something equivalent to Baylor's original data. Of course, you see a whole lot. You see a few thousand trials in this data set. You've got to make a lot of trials. Not only is this distribution correctly predicted by theory, but with no free fitting parameters, if I send in a signal that's 4 times greater, I know what this one ought to be as well, and that one lies on the curve without any more fitting. That seems like a good theory. Let's go back to that superhuman vision. First of all, Baylor and his colleagues, they also changed, now you can do anything. You can change the color of that incoming flash of light and measure directly the sensitivity curves of over 100 primate cells. And what do you know? They fall into 3 categories. There's 3 different kinds. Within each category, they all have the same sensitivity curve. That's Thomas Young's prediction, which some Young guessed in 1801. Then they used those curves to make that prediction of color matching, which I described earlier that was so successful, pretty good. We've tied up some loose ends in part 1 of this talk. Can we go now? Is that all? Well, hang on a little bit longer. We get something more. Once you really believe in the lumpy nature of light, then you can see how to make some more steps forward. Anybody can walk into Walmart and pick up a binocular, and that gives you superhuman vision. And you diddle it around, you get a microscope, that's superhuman vision. But even the most expensive microscope in the world still can't resolve objects that are too close together. If 2 objects are closer than the wavelength of light, then you won't be able to see them. That was dogma for over 100 years. People worked out the optics, and that's how it goes. And that's really a pity because visible light has a kind of a long wavelength, kind of too big to see the things that we really want to see inside of cells. You've got little motors, little molecular, single molecule motors in your cells. They're walking along tracks. Every time a muscle contracts, it's because these single molecule motors are walking along their little tracks. Unfortunately, they're too small to see. They're smaller than this diffraction barrier. So it's not even enough to be superhuman. We want super resolution microscopy because of this randomness thing that we already saw. For instance, here's one of those molecular motors. You can't see the track that it's on, but the motor's been labeled fluorescently. And it's making a rather fat spot there in the microscope. Here's a video. Watch closely. Step. Step. That thing is taking little steps, but it's hard to see what's going on. It's hard to know what the step was because the steps are so much smaller than that broad smear of light, which is the best that any microscope can give you. But if you take any one frame of that video and make a histogram of position X and Y versus how many photons you got, there's a bright spot somewhere and then it tails off. This distribution is fat, it's a couple 100 nanometers, but nevertheless, you can fit this to the shape that you know it has to have and find out where its center is to way greater precision than this width. If you collect enough photons, you can get as much precision as you want. You can get fluorescence imaging at 1 nanometer accuracy. And when you graph the progress of that motor, here's time, here's position, it went off the edge of the screen, you see step, step, pause, step, pause, step. You see these beautiful steps. They all have the same size. This thing is making steps of 70 nanometers, and it's pausing by certain amounts. And even the lengths of these pauses are telling us something interesting about the mechanism by how this machine works, something we couldn't have seen if we hadn't understood superhuman vision. You could do better than that, too. You can take that same idea. Oh, yeah, by the way, my friends who invented this like funny acronyms, so I called it Fiona, because that stands for fluorescence imaging at 1 nanometer accuracy. Anything newer than that? Oh, yeah. You can use that same idea in a different way to make a family of techniques that got called Method of the Year in 2008. Here's a conventional fluorescence microscope. You see some stuff, some fibers, some little objects. It's kind of crappy. That's the best you can get because these things are too small to see with visible light. Until you apply that trick that I gave you on the previous slide, then the same image looks a whole lot better. In fact, it looks so good, you can take a little piece of it and blow it up and it still looks good. And you can see things that you couldn't see before, like the fact that these filaments are actually smaller than those red blobs, something you couldn't see before. So understanding the lumpy statistical character of light has led us to microscopy methods that are opening our eyes to new things we couldn't see before, and that's good spycraft, I think. Right, so many clues, including even things about our own personal vision, led us to a surprising conclusion about light itself. If we didn't have that understanding, we wouldn't have been able to imagine how to break the resolution barrier. I like that. I want to let Heinz Pagels have the last word. He says, I like to browse in occult bookshops. The factual contents of those books are almost entirely fraudulent, but what is not fraudulent is the depth they reveal of the human need for a spiritual connection to the forces of existence. That makes sense to me. So I told you some stories, and how do you know that they're different from occult voodoo? Well, we started out with some real reality. That's a good step. That led us to a paradox whose resolution turned out to be real fruitful. We followed our hero as he teased out the existence of unseen actors and mechanisms decades before their direct proof, using some mathematical ideas, and they weren't very difficult. And we discussed how you test a theory and why you should test a theory. Okay? It takes a lot of effort. It's not an armchair activity. This is called scientific research. It also costs money. We learned some lessons that translated into methods that have paid off in unexpected ways. And this is just the tip of the iceberg. I just chose 4 for you, but there are lots of other examples. And we also learned something deep about physics, something about the character of light that people didn't used to know. We got a connection to the forces of existence, and I like that too. So, you know, if there are any young people in the audience, you may be wondering, well, can I really do this? And I'd like just to emphasize once again, if you've got a personality type that's meticulous and likes craftsmanship, and if you just absolutely have to get to the bottom of things that don't fit, then There are a lot of urgent problems that need to be solved. Okay? And you never know in advance which of those problems is just about to give way to a breakthrough, and we need a lot of agents in the field so we can cover them all. And thank you very much.